Okay, so why we look at linear functions or graphs of these functions, one of the reasons is let's look at this. This is just y equals 11x. It could be that you earn $11 per hour. So if you work 5 hours, you're going to get $55. If you work 10 hours, or 10 times 11 here is $110. If you work 15, and you can read this straight from the graph, if you work 15 times 11 is $165 you're earning. But this is only going from x equals 0 to 15. If we want to go further, what if we work in 30 hours? Well, maybe it's up here somewhere, so it's about $330, but we can work it out. We can change this, and we can maybe make it 35. And now we can read it straight off the graph, and we can assume 11 times 30 is 330. 11 times 35 is 385. It just gives us that value. This is a relationship. Now, that was a really quite easy one, or easy relationship, but that relationship holds. Suppose we've got this relationship, and this is the cost of hiring a restaurant out, and it costs $400 plus $15 for everybody that comes. So if one person comes, it costs $415. If two people come, it costs $430 because 2 times 15 is 30, so 430. If three people come, it's $445. But instead of always substituting into this formula, we could draw a graph, and if 30 people come, we could just read it straight off the graph. Okay, it's going to be this amount. What if 70 people come? Well, we can change this function and do it for 70 people. Okay, or we can substitute into that. But once we've got this linear model, we can see what's going to happen in the future. We can just follow this linear model. If 80 people come, it's going to be that. We actually don't need this anymore. Okay, 80 people come, it's going to be out here. If 100 people come, and we can zoom out. Okay, what if 120 people came? Oh, well, we could just extend this or extrapolate that line. That's why we deal with modeling or modeling. This is one that is quite pertinent to today. This is a different type of graph. Now, at the moment, this looks like a pretty boring graph. It looks like a straight line graph that's pretty flat. But this is a weird formula that I've got over here, just called an exponential. And if we zoom out, it still looks flat. It still looks flat. But we can start seeing now, it looks pretty flat, but you can just see it starting to curve. Now, this is an exponential graph, which you've probably been seeing lots of lately because of the coronavirus. It spreads exponentially. It's very much like compound interest. That's the power of compound interest. It's an exponential graph. So once it starts rising, it rises very rapidly. And you can see now it's starting to rise very rapidly. And obviously now it's not just rising rapidly, it's rising, unbelievably. And that's what when you hear people say it's rising exponentially, this is what it means. And if we zoom out even more, we can see that the rate of increase is just, it's getting larger and larger and larger. So that's why we look at linear models or models of things. We can extrapolate. So at the moment, they've got all these models about the coronavirus, and they're saying, okay, if we don't do anything, this is what is going to happen. That's why the government is putting in some fairly rigid rules around it to try to stop this happening. If the government doesn't do anything, this will happen. We're probably here at the moment. So if the government hopefully can do something and this will flatten out, that's what, when you hear them saying flattening the curve, maybe you've heard them say that. I'm a maths teacher, so I've heard them say that. When you hear them say they're trying to flatten the curve, they're trying to make the curve flatten out and do that. Okay, so that's why we study graphs of linear things where y and x are somehow related with some formula. Thanks.